Welcome to our physics class. This is Chibuzor Mathphysics, and this will be a revisions part 1 on thermal expansions. We've been able to establish the meaning of thermal expansions on our previous videos, where we talk about how materials, especially metallic materials, tend to expand or contract when heated. So now we are in revision questions as students prepare for their final examination for this term 2, and I would like us to kick off with the sample problems on thermal expansions. So pay very good attention so that you know how we deal with these questions. Of course, you can refer to previous videos on where we do most other exercises and problems that are relevant for these coming examinations. So this is the first question on thermal expansions for our today's revision. Initially, a copper wire has a length of 10 cm at 25 degrees Celsius. It was heated up to a particular temperature and it increased its length by 0.00255 cm. Determine the final temperature of the copper wire. Of course, we know that when we were talking about thermal expansion, I mentioned that it's all about how objects or materials expand or contract when heated. So we have a copper wire that has a length of 10 cm at some degrees Celsius, which is initially it was 25. After heated up to a particular temperature, it then increased its length by 0.00255 cm as indicated. So you are to find the final temperature of the copper wire. So the first thing that you will need to do is to have your formula. Of course, we know the formula for finding this temperature, like I have mentioned in our previous classes. We know our formula. Usually it is the final length. So the final length must be equal to the initial length into 1 plus alpha. This is alpha delta t, And in our previous videos, I had already helped you guys to derive this formula. So you can actually refer to the previous video on how we derive this formula. So now, how can we handle this question having seen the formula that we are supposed to use in the following question? So this is the formula that you are required to use to find the final temperature of the copper wire. What we are looking for delta T. So we need to rearrange this equation. We can start by dividing both sides by L0 because our target is to ensure that delta T is on one side. So if you divide both sides by delta T, let's say that we divide this side. We divide the whole of this side and the whole of this side by delta T. What happened, by L0, we divide this by L0. So you will observe that this L0 will cancel with this L0. So that what you are going to have now is going to be L all over L0. And this is equal to 1 plus alpha delta T. That is the change in temperature. But still, this is not the equation we want, because our target is to ensure that delta T, like you have seen here, our target is to ensure that this delta T, is on one side. So we want to ensure that that happens. Delta T is on one side. So what we are going to do next, it will be to take this one to the other side, so that we are going to have L divided by L0. When we take this positive 1 to the left hand side, it will become negative 1, and this will be equal to alpha delta T. So at this point we will continue because we still have alpha on this side, and that is not what we want. So we can divide both sides by alpha. So if we divide this side by alpha and also divide the whole of this side by alpha, so what happens now is that we can actually take this up a bit. So what happened now is that what we are going to have will be L divided by L naught. Of course, this is minus 1, and all this now, let's say all that now, all of this is going to be divided by alpha, and this is alpha, and all this is equals to now delta t. So now that we have our formula delta t, it will be good to ask what is delta t. We know that delta t is nothing but the change in temperature. So this delta t implies that we are looking for the final temperature minus the initial temperature, which is T naught. So rewriting our equation, we will have L all over L naught minus 1. All of these divided by alpha is nothing but T final minus T initial, which is the final temperature minus the initial temperature, which is what we are calling delta T. That is exactly what we mean when you say delta T. We are referring to the final temperature minus the initial temperature. So at this point, we can be able to determine the final temperature of the copper wire. Bear in mind now that since we have this, let me get some space here. What we are going to do now is to go ahead to determine the final temperature of the copper wire. So therefore, the final temperature, which will be represented as Tf, is nothing but L minus L naught and divided by L naught minus 1, and all this will be divided by alpha then plus T naught. What I have done is simply to take T naught to the other side, because when we take T naught to the other side, we assume that this T final is on the right hand side. But since we are looking for T final, we will simply have L divided by L naught minus of course this is minus, this is minus. Pay attention to this. That is minus 1 divided by alpha. So now you can go ahead and plug in the values as given in the equation. We know that initially a copper wire has a length of 10 centimeter, and then it increased. Maybe I scroll down a bit. This is what we have. Initially, a copper wire has a length of 10 centimeter at 25 degrees Celsius. It was heated up to a particular temperature, and then it increased its length. So this means that we have the initial temperature and the final temperature. So we are going to add the two temperatures. When you add the two of them, what you have is 10 plus 0.00 this is plus 0.00255, and you will observe that what you will have will be 10. If you add this, it is going to be 10 plus 0.0255 centimeter. So now this is going to be our final temperature, the final length as indicated, the final length, because we know the length is 10 centimeter at this degree Celsius, and it was heated, then it increased the length to this 0.0. You add the two lengths up so that we are able to get the final length. So the final length is nothing but 10.00255. So at this point we can, let's get some space here. And then substitute the values. We can get that space and then move this a bit. So we just substitute the values. Our T final, therefore, our T final is going to be, we know that T final is length like you have here. So the final length is nothing but 10.00255. Divide this by the initial length. And we know the initial length is given as 10, so it is divided by 10. Minus 1 like you have seen here, minus 1. Divide all this by alpha. We divide all this by alpha particles. That is, we know that alpha is a thermal coefficient of linear expansion, and for alpha, in this case for a copper, it is 17 times 10. We know that is always given, so it is 17 times 10, negative 6 raised to negative 6, and this is per degree Celsius. It is per degree Celsius. Now we can get some space here. So this is plus what you have here, which is T naught, and we know our T naught is the initial temperature as it is given. It is 25 degrees Celsius. So this is 25 degrees Celsius. So what will be the final temperature when you put the whole of this in your calculator? It is 10.0, this is 00255 minus 1 divided by 10, and all this divided by the thermal coefficient, which is alpha, and it is given as 17 times 10 negative 6 per degree Celsius plus 25. You will get your final temperature to be 40 degrees Celsius. And this is how you compute questions related to thermal expansivity. So let's continue in the next video with some relevant examples or sample questions like this that will require your knowledge of thermal expansion to find solutions. I hope you have enjoyed, and if you are joining us in this video, don't forget to click on the subscribe button so that you are going to be notified in the subsequent videos.